So welcome back. In this lecture, we officially start the second part of the course in quantum mechanics and quantum chemistry. So basically, we are going to move steps towards quantum chemistry. And in particular, we shall begin walking towards a theory for the quantum theory for the hydrogen atom, and then make comparison with the classical theory for the hydrogen atom. So we begin by doing some atomic physics. We then spend some time to figure out what happens if we try to generalize this basic understanding to atoms that are more complex than hydrogen atoms. And we basically arrive to sort of recapitulate and recompile the information contained in there. The physical origin of the periodic table, if you want. Mendeleev periodic table. And after that, we go more specifically into molecules and define a theoretical framework for molecules and approximation methods that are needed to describe molecules, and perhaps a couple of lectures on the theory of hydrogen bonding. Sorry, chemical bonding. Okay, so that's a lot of stuff to do. We better get started. Today, we move just, we do some preparatory work. And in particular, today we discuss of quantization of orbital angular momentum. Okay, so quantization of orbital angular momentum, which is a tool that will enter the description of electrons propagating in central potentials, because as we know from the classical discussion, the motion in central potential classically conserves orbital angular momentum, so you expect that to be fundamental ingredients also at the quantum level. So we have already accumulated enough background in quantum mechanics to basically apply basic rules to define the quantum angular momentum operator. So let me remind you the definition of the classical angular momentum, which in turns, we can define this in terms of a simple rule that enables us to, compute each component of the angular momentum. That's a simple, table rule that allows us to, mnemonical tools we can use to evaluate the three components of the vector product in terms of simple operation between the components of the vectors. So in other words, this is E1 multiplying YPZ negative Z PY plus E2 multiplying ZPX negative EX Z plus E3 multiplying XPY negative Y PYX. And there is a problem here. Okay, so let's check E1 YPZ Z PY. E2 is ZPX XPZ. There was a mistake here. XPZ. And E3 is XPY YPX. Otherwise, these would be simply be commutators. So now you can disregard this. It's just a simple little rule to remind ourselves how to compute vector products. So this is a classical expression. Now we want to work out the corresponding quantum operator. So we want to quantize the angular momentum operator. And remember, the idea is very simple to quantize an operator. You have to, first of all, remember yourself to put hats. And therefore, there would be three operators that classically are called Lx, Ly, and Lz. And you want to quantize each of them. And in particular, Lx is going to be y. Remember the rule, negative I of h bar d by dz, negative z. Well, we could say we can pull out the i's everywhere. So I would say negative IH bar y d by dz plus IH bar z d by dy. Then I have the quantum version of the y component. It's going to be negative IH bar z d by dx plus IH bar x d by dz. And the last component, the z component, is going to be negative IH bar x d by dy plus IH bar y d by dx. Okay, so these are the three components of the magnetic, the angular momentum orbital angular momentum operator. And there's nothing deep in whatever we've done so far, other than apply the quantization rule we already discussed. Now, it is now an important question is to address is whether can we measure all of them, of the three components, with simultaneously with arbitrary accuracy, simultaneously and with arbitrary accuracy. In other words, what can we do with them? Are these a set of operators that have a joint set of eigenstates? That's an important question, because we already have seen that in many cases, quantities that can be determined classically, like momentum and position, cannot be determined simultaneously at the quantum mechanical level. So it's quite important to make sure we can do this. So how do we know this? We compute the commutators. So what does it mean to compute the commutators? It means to evaluate all three of these relationships. Okay. And as usual, this means taking a test function. In practice, it corresponds to take a test function, let's call it f of x, and applying in sequence the two operators and in the reversed order to the test function. And simply see what happens. And whatever is the result of this double differentiation, this commutation relationship is actually the right-hand sides are, the right-hand side to each of these equations. So in the following lecture, I will only consider this, and because all the others are really completely trivial. So let me just here downstairs let me here remind myself that this is basically x times negative IH bar d by d, oh sorry, it's not x, it's y d by dz, negative z, negative IH bar d by dy, apply to Ly of f of, which is this one, that is z d by, okay, negative IH bar z d by dx minus negative IH bar x d by dz, and that's Lx times Ly to f, which of course I don't have room to write it here, and then I have a negative of the same thing in the opposite order. So negative IH bar z d by dx negative IH bar, oops, x d by dz, and this is Ly, and then I put Lx, which is y, negative IH bar d by dz, negative z, negative IH bar d by dy, apply to my function f. Okay, now for sake of simplicity, for this point on, I will call d by dx dx, d by dy dy, and so on and so forth. So I will save some, some fraction of seconds in writing. Okay, so let me collect everywhere. I can collect all these negative IH bar factors that appear everywhere. There are two of them in each product. So this is going to be negative H bar squared, and then I put the graph. And then I'm going to leave the first term there, y dz, negative z dy, That's the first term. And let me act on the second term. So that's going to be times. I have two terms here. First is z dx of f negative x dz of f, and I'm covered the first line. Then I have a negative z dx minus x dz, acting on, I have y dz of f negative z dy of f, and I cross this. Now, each of these two terms will generate 4 terms. So let's be a little bit patient and we'll survive this horrible calculation. So let's consider this 1, 2, 3, 4. So let's first look at 1, 3. It means that I have to evaluate y dz of z dxf. Then I have 1, 4 negative y dz x dzf. Then I have 2, 3, which is a negative this z dy z dx f, and then I have a plus z dy x dzf. And that is the first half of the calculation. Now I have a similar, so let me check that I'm not making a big mistake. Y dz, this is the 1, 3, y dz, z dx, then I have 1, 4, y dz, x dz, okay, then I have 2, 3, z dy, z dx, then I have 2, 4, z dy, x dz. Okay, now I have 4 terms from this. Let me now cancel these numbers here and put it here. 1, 2, 3, and 4. And I get a negative z dx y dz of f, and that's the 1, 3. I get a negative, a positive z dx z dy f, that's the 1, 4. Then I have a positive x dz y dzf, that's the 1, 3. No, these are already 2, 3. Okay. And then I have a negative x dz z dy of f. That's the 2, 4. Okay, hopefully I'm not making big mistakes because it would be hard to correct, unlike in a real lecture where I have boards that I keep track on. Here, once I erase, I take my chance to be able to correct possible trivial mistakes that I might leave behind. So let's cross fingers. Now, what I'm going to do now is to make some simplification. For instance, look at this first term here. The z, this is probably the only case where I should not be making the simplification. Okay. Erase once again. So let's look at this first. Here. The derivative with respect to z will pass through x. So what I can do, I can move x on the other side and put the second derivative with respect to z. The same is happening here. Unfortunately, okay, let's see. Y dz times z dx. Y dz x dz y dy z dx. Okay. Now the same happens here. This derivative with respect to y can be moved through, so I have a squared dy. Same happens here. Dy can be moved here. So here dy can be moved here. The same happens here. Y can be moved across. Let's see. Y can be moved across. Same thing here. Z can be moved across. So instead of z, I can write z squared. Okay. Then what about here? Y can be moved across. Y dz. And okay, this is not, yeah, this cannot be moved because this is acting on all this. Okay. Okay, good. So now you already see some cancellation take place. For instance, let's look at the ones where I have second derivative with respect to z. So this has a second derivative with respect to z. This has a second derivative with respect to z with the opposite sign. That's good. I have a negative z square here, and I have a negative positive z square there. So these two will also cancel. And then let's see what happens now. So let's continue. Here, I will get negative h bar y dx f plus yz dz dx. F, I'm spreading out this term here, expanding this, plus xz dy dz of f, I'm here, negative yz dx dz of f, and I already see another cancellation. And then I have another two terms. I have negative x dz, negative x dy f, and a negative xz dz dy of f. Now, if I've done things correctly, there should be major consolation now. In fact, there we go. This cancels with this. And this cancels with this. So, luckily enough, I've done calculations correctly. I can erase this now, take my chance. And if you do, you end up with the following results. Negative h bar squared y dx negative x dy of my test function. Oh, things start to make sense because I know the structure, this crossed position derivative structure. It is resembled of the structure of the orbital angular momentum operator itself. In other words, what I can do now is to do the following. I will put an I here, h bar, and write this. And so basically, let's see if the sign is correct. I put the I. Now I guess there's a minus here, because this minor have to cancel. Yeah, that's correct. Now, so what this is actually telling me, let me now change color here, is that this is nothing but I h bar LZ of f. So basically what this calculation led to was this important result. And you can propagate this to all the others. In other words, if you do exactly the same calculation with all the three different commutation relationships, then what you actually come up is a set of commutation relationships that have the same structure overall. So an easy way to memorize this is to do Lx, y, and z, and draw a triangular permutation diagram. So what does this is telling me? Sorry. What this diagram is telling me is that if I do commutation of Lx and y, I get Lz, Ly, Az, I get Lx, Lz, Lx, I get a y. So no, you cannot measure all three components of the orbital angular momentum simultaneously. The measurement of the second component will destroy the information about the first, and you will get a non-vanishing commutation relationship. There will not be any joint eigenbasis for these operators. And I would like to note that similar situation was inferred by looking at the Stern-Gerlach experiment, where we came to the conclusion that mu x, mu y was not zero, mu y, mu z was not zero, and mu z, mu x was not zero. Now, we did not infer the value of this commutator just by looking at the results. But also in that particular case, we were noting that it was never possible to measure any pair of components or magnetic moments with infinite accuracy. So there were similar commutation relationships and uncertainty relationships are to be expected. However, there is one thing that can be noticed by doing explicit calculation, and this is indeed a very long calculation. If you want to get handy with partial derivative, do it, but it's really, really long calculation. And it's the following. L squared Li equals 0 for all I equal 1, 2, and 3, or x, y, z. So in other words, it is not possible to determine more than one component of the orbital angular momentum simultaneously. But it is possible to determine simultaneously one component and the square, or if you want the modulus square, of the orbital angular momentum. Well, clearly, L square is the operator L acting on L times whatever comes around, right? So there is, in fact, a set of maximally commuting. There exists a set of maximally commuting, a set of common eigenvalue states for L square and say Z for these two operators. And Z. Or you may choose any other component, but just one of the orbital angular momentum. You can choose X or Y, but you have to pick one. You cannot find a common set of eigenvalues, of eigenstates of L squared, and more than just one component of the orbital angular. So this finding leads to the next question. So before we go to the next question, actually, let me just write it. So I can find a set of states with eigenvalues of L squared and eigenvalues of Sz. I can denote it with a corresponding eigenvalue. And what are these states? They are the states that if I apply L squared on the eigen of this, I get EL squared, EL squared, ELC. And if I apply LZ,
to the same common set, I'll get Lz, the eigenvalue of Z, times EL squared Lz. So what is this notation? This is eigenvalue of the operator. I'm labeling the states according to their eigenvalue with respect to L squared and to respect to Lz. So what E of L squared is the eigenvalue, one specific value. I could have called it A and remember myself that A referred to the L squared operator, or I could have called it whatever. But E L squared is the eigenvalue of the L squared operator, and LZ, ELZ is the eigenvalue of the LZ operator, as clearly specified by this equation. Okay? So the next question that we might ask is, what are those eigenstates and eigenvalues? So, in other words, can we diagonalize simultaneously this operator explicitly? Or, in other words, just as much as like you can, it so happens that these two eigenvalue problem, which in fact are differential equation eigenvalue problem, just as much as the Schrodinger equation, can be solved analytically. Therefore, in position representation, it is possible to find the eigenfunctions of both L squared and Lz. These are called the hypergeometric, hyperspherical harmonic functions. The name is quite fancy. Let's see what they mean. Okay. To this end, it is convenient to resort to spherical polar coordinates. So in other words, rather than using X, Y, and Z, I pick up my sphere and I use theta for my point on the sphere. This is my point P line on the sphere. I project it down here. Right, this will be X and Y, and my drawing is admittedly very, very bad. Let me try to draw this in a more convincing way. It's even worse. Fine. Even worse. Wow, I give up. Never be able to do this any better. Anyway, this can be the phi angle. Right? That's a unitary sphere. A point on a unitary sphere is specified by two angles. Then, of course, in principle, I have the distance. So this is the radius of the sphere. In the mathematical background lecture, you must have seen this already. Now, if you represent the operators in spherical coordinates, you get quite complicated equations. Now, I'm gonna tell you how to work this out, how to go and find them. If you look at my teaching, molecular physics, I think it's chapter 5. Yeah, that's what we just said. This is the eigenvalue of L squared. This is the eigenvalue of Lz. I call it E of L and ELLZ for reasons that will become clear later. These are the polar coordinates. This is the Laplacian polar coordinates. And this is the expression of the L square operator. So you can actually work out everything else. And so let me take for a moment this and tell you that, in fact, I'm going to be back in a moment to this. I'm going to move here and say that if you go to position representation now, I get L squared. You can define, well, let's still be abstract for a moment. I go to position representation. So remember, we had the notation, the eigenvalue of L squared. It turns out that you can label the undervalues of L squared with an integer number. Let me call it L and M. This will tell me what the eigenvalue of L squared is, and this will tell me what the eigenvalue of Lz is. And if you solve the equation, which of course I don't ask you to be able to, if you solve that problem analytically, you'll find out that this is actually L, L plus 1, L of M, where L is a number that can be 0, 1, 2, up to as long as you want. So there are infinitely many eigenvalues and eigenstates of the square of the orbital angular momentum. They are labeled by an integer number, and therefore the smallest is actually, so correspondingly, the eigenvalues. So if I write here the values of L and the value of h bar square L, L plus 1, I get 0, 0, 1. Here I get 0, 0. When I get 1, I get 1 plus 1 is 2, so it gets 2, h bar square. 3, 3 plus 1 is 4 times 4, 3 is 3 times 4 is 12 h bar square, and so on and so forth. So it's almost like when L becomes very large, then the eigenvalues of L square are just capital. Say the eigenvalues become just L squared, but for small values, they're different from L squared. So maybe it's convenient to plot this rather than in the table. Let's put it down into a graph. So I get 0, 1, 2, 3, 4, so on. This is L, and this is h bar square L, L plus 1, which is nothing but E Lz squared. And I get 0. When L is equal to 1, I get, like I said, 1 plus 1 is 2, times 1 is 1. I get 2. 2. And when L is equal to 2, I get 3 times 2 is 6, and so forth. So when you go very much high moment, for very large values of L, clearly for very large values of L, the eigenvalues are almost h squared L squared. You know, basically tells you the angular momentum is quantized in units of h bar. At small values, they are not. There's this, you know, overall offset here. Now, how about the eigenvalues of Az? Now, it turns out that the eigenvalues of Az depend also on the value of m. So in other words, m is not any integer. M is an integer that goes from minus L to L in unit steps. So m is an integer that goes from the maximum possible value to the minimum values in units steps. And LZ, Ln is nothing but h bar m L. Okay, so maybe it's convenient to think about this in the following terms. You have a maximum value. It's almost like, so basically it's almost like, you know, you have a vector of unit L and you can sort of look at this component in a quantized way, right? So this is all the components upstairs, a little bit smaller component of the Z, a little bit small component of the Z component, and then you know, quantized components. But there's something counterintuitive because, you know, the modulus of a vector in classical mechanics would be L squared, while in quantum mechanics, the corresponding eigenvalues are h bar squared L, L plus 1. So this is typical feature of quantum mechanics. Nobody really knows why it's what it is. And we just have to take it as a mathematical fact. So these are the eigenvalues of the both operators. And it means that if I take the differential form of the L square operator, which in polar coordinates looks like this, I can find a function which depends on phi and theta, such that these two relationships here are satisfied. LZ. And like I was telling, these functions are function of theta and phi, and they're called the spherical harmonics, or spherical harmonic. I would say spherical harmonic, not hyperspherical harmonics. That's something from my previous background in nuclear physics interfering with my lecture. Hyperspherical harmonic, spherical harmonic in many dimensions, which we are not interested in this course. And as you can see, this is an explicit expression. What you find here is what is called a Laguerre polynomial, which depends on the index m and l according to this combination. And in this case, of course, instead of x, when you want to spell down this, you have to put cosine. So let's take some example. I'm going to write it here and show you. So let's say n is equal to 0. Then clearly, if L is equal to 0, then obviously M must be equal to 0, because M, remember, goes from minus L to L, and if there is L is equal to 0, M must be 0. So my harmonic function is this. And if I go here and see what it is, I get 0 here. 0 minus 0 factorial is 1. 0 plus 0 factorial is 1. So I get 1 over root of 4 pi. And then let's continue. What about this? I have a Laguerre polynomial with m and l equal to 0, so that's going to be m to the 0 is 0, 0 factorial is 0, 2 to the 0 is 1, this is 1, and this is 1. So this is just it. And in fact, this is a correct normalization, because if I perform the integral from d phi, d theta, sine theta, from 0 to pi, from 0 and 2 pi of 1 over 4 pi modulo square, which I can take square, that's the normalization of this function, I get 1. So let's take one more example. L equal 1. Then in case m can be 1, 0, and minus 1. So let's, to be specific, take L equal 1, m equal 1. Then we can so just to make sure you're on the same footing, what I just said is that y0, 0 is 1 over 4 pi, which is the correct normalization. And now I'm using L equal 1, and it will be 1, 0, minus 1. So L equal 1, m equal 1. And go now and apply the solution that I told you. I get y 1, 1, theta phi is equal to minus 1 to the 1, which is minus 1. I'm going to show you the result in a minute. So I'm just going to write 2 plus 1 is actually 3, 4 factorial, 1 minus 1 is 0 factorial, then it's 1 over 2 factorial is 2. Then I get P11 cos theta, so it's minus 1 to 2. 1 factorial is 1. 1 minus cos theta squared times 1/2. And then I have the second derivative with respect to cos theta of cos theta squared minus 1. So basically, if you substitute 1 and 1 in these positions here, and you write things explicitly, you come up with this equation. So that's second derivative with respect to cos theta of this actually goes away. This is not there, and you get a cos theta dependence. So basically, what I'm telling you is that by choosing different values of L and M and bringing them in here, you can reconstruct different functions, and these functions are in fact the solution of these differential eigenvalue problems here for different values of the eigenvalues. Now, I want to emphasize one thing. How does functions look like? Well, clearly, when L is equal to 0, M is always equal to 0. This dependency here is trivial, because see, this particular solution contains no dependency at all with respect to neither phi or theta. That means that if I were to, I could sort of represent graphically this as a sphere. Why as a sphere? Because basically, in any points of the sphere, regardless of the value theta or phi, y is always equal to 1 over root of 4 pi everywhere here. However, if I look at the other solutions, you get the dependency on both theta and phi in general. And if you look at the L equal 1 and M equal 1, you get a dependence on theta through cos theta and a dependence of M through a phase. Phi. Now, if you look at the square modulus, in other words, some kind of probability, we'll discuss later what kind of probability we're looking at, well, then the phase doesn't appear and you get a function of cos theta squared. And basically you can represent this as a function that changes with cos theta, and if you were to plot this, maybe using Mathematica or so, you discover that you can represent this as something like this. It is large near the pole, very, very small when theta becomes almost 90 degrees, and becomes large again when you get back to minus pi, but it's spherically symmetric because any value of phi will give you the same result. Symmetrical and rotational along these axes, because any value of phi will be the same, will give you the same formula. So I encourage you to go back to this expression here and trivially plug in some numbers. Another thing that I encourage you, no, I don't encourage you to do that. So one thing that you should be able to do that if you really want to push is to show that if you take this particular expression here and you apply to it, say, this operator, you have to do a lot of derivatives. Very good. But after you have done a lot of derivatives, you'll discover that the result will be still in the form of the same combination multiplied by a pre-number, and that this pre-number will be precisely this factor. Well, I can do this in the most trivial case, the case in which y, L and M are 0, just to convince you. In fact, in this case, it all would amount to say that L squared of y 0, 0 is, I expect this to be h bar squared 0 times 0 plus 1, y 0. In other words, to be 0. And in fact, you can verify, because if this is a constant, this depends on derivative either with respect to theta or with respect to phi. Let me show you. Each and every term here contains a derivative either with respect to theta or with respect to phi. So since this doesn't depend on either on theta or phi, this term acting on this is a derivative of a constant, and it will give me 0. So this is in fact an all these things of L squared. Of course, when you go to higher values of L and M, then you have to, you cannot simply guess what the solution is. And thanks to the very powerful mathematicians that were there at the beginning of last century, people were able to solve this equation and diagonalize the operator at all the states. It's not our task to do that. It's for mathematical physicists to do that, and people have done that back in the 20th century. So we can rely on their results. Okay, so summarizing, today we introduced the concept of orbital angular momentum in quantum mechanics. We calculated their commutation relationship and went as far as to determine the complete joint set of eigenstates in polar coordinates. This will be essential to describe later the concept of molecular orbital. So try to familiarize with what is a L square and what these functions sort of look like. You don't need to remember them by heart. I don't know them by heart, but you need to remember that they depend on L and M. You need to remember the values of L that are allowed and the values of M that are allowed. And you need to remember the dependency is between, that this function depends on cos theta, and on phi. Okay? So good luck with all of that, and we'll see you soon.